Hello everybody, I'm Nicolae Tusinschi from OneSpin. I'm a product specialist design verification, and today we're going to talk about formal verification of floating point hardware with assertion-based verification IP. What we're going to talk today is about a short introduction with the floating point arithmetic, what are the current solutions existing in order to functionally verify the floating point hardware, and what is the solution from OneSpin with formal verification with assertion-based verification IP, and results from internal testing and customer usage of the verification IP, and in some conclusions. So what is floating point arithmetic? So compared to fixed point one, it covers a wider range of values, and there is no loss of precision, higher accuracy. But the drawback, it comes with as well with the drawback, is it needs to, the hardware that is developed in order to implement this floating point arithmetic is more complex, and it is notoriously hard to verify. So here we have the IEEE with a sign, exponent, and mantissa, and half, single, double precisions from 5, 8, 11 bits for exponent, and up to 52 bits for mantissa. So what are the current solutions existing in order to verify? So traditional simulation is really not feasible to exhaustive to do the verification of floating point arithmetic. And simulation misses bugs, and many implementations are dependent, and the corner cases are related to this implementation dependent. So yeah, simulation is not feasible, and it also takes a lot of effort in order to set up the environment and to have a good full test bench in order to verify it. And another solution that exists on the market is sequential equivalence checking, where the RTL, the floating point arithmetic implementation, is compared against the reference model. This model can be another RTL, or it can be a reference model developed in C++, System C, but these reference models needs adaptation, and the high effort is does not pay off, and it has a little reusability, and it requires a detailed understanding of both implementations of the System C, C++, or RTL reference model, and also it requires knowledge about the floating point arithmetic you want to verify. And here, how to verify this with formal assertion-based verification IP. So our customer, Xilinx, tried to verify with existing solutions, but ran into usability and convergence issues. So together with Xilinx, here we in OneSpin worked in order to develop new solutions, in order to reduce the hassle and to get decreased runtime. So yeah, how does this look in OneSpin? So the floating point assertion-based verification IP. So it comes with a SystemVerilog package, IEEE functions developed, and data types inside OneSpin. There is no reference model required in order to verify the floating point arithmetic implementation, and the design, the end user doesn't require knowledge so he requires minimal knowledge in order to perform this verification. So how this verification IP comes with OneSpin tool. The special proof engines and strategies were developed to support this arithmetic problem, and also the assertions that are violated can be debugged with floating point data types in OneSpin debugger. So how does this look? So in the middle, we have the OneSpin formal tool, which takes as input the floating point implementation, and the user instantiates the formal assertion-based verification IP. Then the assertion-based verification IP needs to be configured, like the user needs to specify what is the precision he wants, or the floating point has, what are the rounding modes, what is the latency when the result is valid at the output, and And once this is configured, on top of the assertions, formal tool is running the checks. If one of the assertions is failing, the user can debug and also fix the bug in the RTL. Or if it gets a full proof, this means there is no way to violate and the operation is IEEE 5754 compliant. So, as I mentioned before, it's compliant with the standard. It supports half, single, and double precision formats, all the rounding modes and the exception flags, tininess before or after the rounding, addition, subtract, multiplication, absolute value, negation, and all comparison operations are supported. Conversion functions are also included, from double to single precision, from single to half, and it is highly customizable. So, and it also is, if the user implemented the floating point arithmetic in that required some deviations from the standard, this is also highly easily customizable inside the verification IP. So yeah, once the user instantiates the verification IP, in OneSpin tool it's opened a template of this verification IP in which the user has this link as comments to do. So please customize in this specific case, please customize coding of rounding modes. So the user knows from the specification what are the codes for the rounding modes. He needs to specify this in verification IP. For example, 00 for nearest even, 0 up, down, etc. And coming with also, in next slide, is coming the assertion. Once the user instantiates the verification IP, it comes with this property template. So you can see that it is pretty intuitive. So first of all, the user needs to specify the trigger of the current operation. He needs to specify that what are the operands. So what are you, in our case, what are you adding? You're adding op A with op B, and also specify the rounding mode. Also, the user needs to specify when the result will be, after how many clock cycles the result will be valid at the output. And also, it property check the computed expected results with the actual that is seen at the output of the floating point. And also the supported flags are also there. So all of these IEEE functions are coming with a floating point assertion-based verification IP. So yeah, what was the problem with the Xilinx? So Xilinx was running into convergence and issues, and they asked us, and we worked together with them in order to solve this problem. So their IPs are highly customizable, some legacy IPs, and they are supporting, in our case, in the design that you was verified with initially floating point. There was supporting addition, subtraction, multiplication. The tool found a previously undiscovered bug in the module interface constraints, and general and specific scenarios assertions were created. So, for example, operations with signaling or quiet, not a number. And design bugs also previously found in simulation and emulation were captured by the floating point assertion-based verification IP within seconds. So here you can see that some results. So initially we tested this against some open core design. And for example, for addition, subtraction, multiplication, in the open core design we found one bug for subtraction, 2 bugs for multiplication. We set up effort. This means the user needs to set up the properties in order to run the proof, run the checks on them. And the runtime is, for example, in range of 1 minute for this operation. So, for example, we got full proof for addition and failing assertions for subtraction multiplication. These bugs were reported to the open course developer. For Xilinx, the design was more complex, so it also supported like addition, subtraction, multiplication. You can see that there is a big discrepancy between the setup effort. So mainly this discrepancy is coming from the fact that the user, the end user of that verified this floating point arithmetic design, was not familiar with formal. So, And this is the reason why it took a bit with the help of OneSpin to set up the entire verification environment. But when you can look at the runtime, so you can see that the multiplication, subtraction, addition are run in a range of minutes. And we got foolproof for all operations. And after the bug was fixed, we got the foolproof for multiplication. So yeah, but the question that came in is like, okay, but how do I know that I covered the entire design? So how do I know that your assertions, that your verification IP is generating, we are generating the verification IP, are covering the design? So on top of the assertions that are coming with verification IP, at Xilinx we run the quantified formal coverage solution. So it answered the question of how much has been verified, what is the next assertions to write, is my design over constraint from the interface, and you can see on the left side of the slide that the quantified solution is annotating with colors the part of the code. So for example, the verified code means that the assertion is verifying that part of code. And there is an assertion that is verifying that part of code. It's annotated in green. If we don't have any assertion, then we have the verification hole, it's annotated in red. If we constrain it from the interface, it gets annotated in brown. And if the designer is introducing a code that cannot be accessed, it is annotated with black, which means it's dead code. So what are the results at Xilinx? So we run quantify on the assertions coming before the formal with the verification IP. And you can see that we got a high coverage with the generated assertions, but you can ask a question, but hey, but you have a lot of dead code. So their floating point implementation is highly customizable. And due to this configuration that was used for this specific case, some branches, some statements are becoming dead. So this is due to the fact that are becoming dead code due to the parameters. Yeah. And in conclusion, so floating point assertion-based verification IP is compliant with IEEE 574 standard. Solution is really easy to set up and use, and we are glad to help our customers. And it all showed an excellent experience for Xilinx floating point unit project, low effort, uncovered corner case parts within seconds, exhaustive verification of the with foolproofs within minutes, so double precision, taking minutes. It's quite exceptional. And we also got a high coverage on the top of the assertions generated with the verification IP. So there are also some limitations. So there is no support for iterative operations, division, square root, and there is additional effort may be required in order to achieve foolproofs in case there is some deviation from the standard. But we are happy to work together with customers if there is a requirement for division, square root, etc. I would like at the end to thank you, Raviram, Adam Elkins, and Adam Protama from Xilinx, and Sasha Stanenkovic, Stan Bayer, and Sergio Marchese from OneSpin for making this work happen. Thank you very much.